Good morning. Today we will finish up our discussion of polymer science by talking about the way in which micro and nanostructure influences the thermal and mechanical properties of solid polymer materials. So you can have a polymer film is not a homogeneous, or a polymer sample is not a homogeneous block of stuff like a diamond or a single crystal of anything. It can have many different, mainly two types of structures within it. There's an amorphous, there can be an amorphous domain and a crystalline domain, and that is for materials that have some amount of order in the backbone. So a repeating structure that has some amount of order can form crystallites and crystalline domains. It's possible that a polymer is so disordered along the backbone, say it has some branches or let's just stick with branches or an irregular structure of repeat units that can't crystallize. So there can be no crystalline order in that material, and that could be entirely amorphous. So the most crystalline you're ever going to have is like greater than 90% crystallinity, but you're always going to have some amorphous character. So if you have a material, and this is just a square cross section, and I'm not going to try to draw this scientifically, but this is, I guess I didn't have to say I wasn't going to draw this scientifically. You would see that the drawing is crap, and then you would know that it's not scientific. Okay, so this is, let's say, purely amorphous. And you might have this with an irregular backbone. Of the polymer that prevents crystallization or branching, or irregular branching. What do I mean by irregular branching? We won't go into details on this, but imagine you had a structure of polypropylene. And the polypropylene will just draw several repeat units, and we'll have, we usually draw polypropylene looking like this. These are CH3 groups that stick out. Now, since carbon has a tetrahedral geometry, this bond could either be into or out of the plane of the board. And we didn't specify whether it was into or out of the plane of the board. Now, unless you take care to make them either all out of the plane of the board or all into the plane of the board, same thing, it's just reversed 180 degrees, or alternating into, out of, then you have a random structure. So this, if we try to indicate what's called the stereochemistry of this as being random, and we'll get rid of the parentheses so that we don't think that this is a repeating structure. I mean that these bonds are random. This is an example of irregular branching. In this case, it's called an atactic polymer. We're not going to go into any details on how you would make something atactic versus isotactic, where they all come out of the board or into the board, or what's called syndiotactic, where they're alternating. But the point is, you can change the crystallinity of this material based on whether the bonds are all coming out, all going in, random, or alternating. And if there's regularity to the structure, then it can crystallize. If it's random, then it can't. Yeah.
Just to slightly double, would we actually select for a more ordered structure by, say, chiral selecting from racemic mixture of monomers?
So the question is, could we select for regularity by taking a mixture of the monomers that had some well-defined stereochemistry, that is the arrangement of bonds in a carbon atom. We can do that in some cases. We can't do it, and this kind of assumes too much organic chemistry for our purposes. But we can do that in some circumstances. We can't do it here because the precursor to polypropylene is this, which there's no chiral information in this molecule at all. This is just propylene. So we can create a structure, we can influence the structure, whether it's amorphous or semi-crystalline, by our choice of the polymer chain itself. But the best we're going to do is something that we'll call semi-crystalline, and the crystallites could be anything. They could be parts of a spherulitic structure. A spherulitic structure is automatically semi-crystalline because we know that there are amorphous domains in between the snowflake-like branches. Or they could be dendritic structures, or they could be long, high aspect ratio crystallites. They could be any type of crystallites. But I'll just draw them just kind of conceptually like this, where we have the crystalline domains. This is semi-crystalline. And the amorphous domains. So this is crystalline, and it's mixed with the amorphous. The density of the crystalline phase is higher or lower than the density of the amorphous phase? Higher. Intermolecular forces are also stronger because the bonds are packed more closely together than the amorphous domains. Is it possible to have a polymer sample that's entirely entirely crystalline? Say a polymer sample of any appreciable size, like say a few square millimeter chunk of polymer. It's in practice impossible to achieve this. And even if you anneal a sample, if there's any amount of polydispersity, any amount of dispersity, I keep screwing, same thing, but IUPAC doesn't like when I say polydispersity. If there's any amount of dispersity in the sample whatsoever, then you'll have chain ends that don't overlap with the adjacent chain end, so the polymer chains can't pack entirely efficiently. Yes?
So by dispersity, you mean different number of monomers in each chain?
Yes, by dispersity I mean different number of monomers in each chain. Even if you had all the same number of monomers in each chain, that would require thousands or millions of molecular weight of a polymer with thousands or millions of Daltons aligning perfectly with each other or overlapping perfectly with itself to form crystallites, which in practice, you'll never quite get there in a real sample. The most you can get, even with monodispersed polyethylene, you'll only ever get to some asymptotic limit. You'll never quite get to 100%. So typically, 50% crystallinity is a number you might see. Okay, now the thermal transitions of these materials are different depending on whether you're talking about the amorphous or the crystalline phases. If you take a sample that is cooled down a lot, below any thermal transitions, and it's a solid material, and you start increasing the temperature, and you look at me instead of your phone. And you increase the temperature, you start to melt the frozen spaghetti that is the amorphous domains. So when that temperature is reached, which is called the glass transition temperature, below which it's glassy, above which it's like wet spaghetti, you're providing enough thermal energy in the material to allow some number of monomer chains to slide past each other. So you've surpassed the activation barrier to allow the polymer chains to slide past each other. So that's the glass transition temperature, or TG. As you increase the temperature even more, you can cause some of these amorphous chains to have enough energy to form crystallites or to join existing crystallites. And they're not going to do so forever, and not going to do so completely because of what we just described. You can't have a completely 100% crystalline material. That's called the crystallization temperature. And would that be exothermic or endothermic? So creating bonds, that is van der Waals bonds or any type of bonds, if we bring two things together from infinite separation, it releases heat or takes in heat? Releases heat. The bonds form, releases heat. And that's called the crystallization temperature. This is exothermic. And you can think about it this way. Boiling water, so water at 100 Celsius, and you put energy in, you add in all the energy needed for the latent heat of vaporization, so you go from all liquid to all vapor. So you broke all those bonds. That is, you put heat in, that's endothermic. So forming bonds must be the opposite, and that's the best mnemonic way to think about this. Now you have maybe a little more, you have a little bit more crystallinity, then you increase the temperature even more, and eventually you get to a temperature where the existing crystallites and the crystallites that were formed at the TC melt. Yeah?
So TC is actually higher than TG?
Yes, TC is higher than TG. And then you have a TM, transcendental meditation. And that's endothermic. And the tool that we use to measure these properties is called differential scanning calorimetry, or DSC. And what we do is we measure the heat flow into the sample. And if the heat flow is into the sample as a function of temperature, and we won't write any units here because we just want to get the general features of this curve. If the heat flow is going into the sample, then endothermic transitions will be up. And this is arbitrary. You'll find DSC traces for materials, and it's not just used for polymers, it's used in all material science, all nanomaterial science, all material science of any length scale. Since this is arbitrary, you'll often find plots that are reversed, where exo is up, exothermic is up. And it's probably, I don't know, maybe 50-50 in the literature and in textbooks. Yeah.
So when we say exothermic, what's our frame of reference? We're talking about into the system? a system that's exothermic is pumping heat out, or our lab is pumping heat into the system?
Maybe if I draw it, it'll make sense. Okay, so we're starting here. So no heat is going into the system. And then what we have at some temperature is a change in heat capacity. And this change in heat capacity is the difference between the glassy state and the rubbery state of the amorphous domains. So this is a change in the heat capacity that occurs at Tg. Then at some transition, we have an exothermic feature, which is the crystallization temperature. And as we increase the temperature even more, we have an endothermic transition, which is Tm, the melting temperature. Now, how do we measure the heat flow? We have a sample in one pan of the apparatus, and then we have another sample, or just an empty pan with a known heat capacity in the other. And what we do is we supply enough energy in the form of heat to our sample so that the two temperatures rise in concert. So they rise together, and we know how much we've added because we know how much more or less energy we had to add to the sample in order to keep the temperature rise the same. So we always do this measurement in reference to an empty sample or a sample with a known heat capacity, or that's not going to undergo thermal transitions in the range that we care about. Otherwise, that would be a huge problem. Okay, does that answer the question?
Kind of complex. I need to think on it a lot, but it's just simply, if we say endo is up, it becomes more endothermic or less endothermic as it approaches crystallization. You said crystallization is exo, but exo with respect to what? Is the lab giving out heat into the sample?
The lab or the instrument is not supplying as much heat there because heat is coming out of the sample.
Perfect, thank you.
Yeah.
So it's like a net sort of because if it was like exothermic, I would assume that the heat flow would be on the negative, like down on the negative y-axis.
We can define the directionality of the heat flow any way we want. So the thermal properties of a polymer have a dramatic influence on the mechanical properties. So we know that if we melt a piece of plastic, or if we have it's a hot day and there's like we've got, well, okay, let's say gum in the gum wrapper is a lot stiffer than gum in our mouth. So we know that the thermal properties of materials have a very strong influence on the mechanical properties. So what happens to the mechanical properties as a function of these thermal transitions? And we will we'll plot the modulus in units of pascals, that's Newton per square meter, as a function of absolute temperature in Kelvin. And this will be for atactic polystyrene. And this is the random polymer that I drew before. Atactic just means random in terms of where the side chains, where the pendant groups are pointing. Atactic random polystyrene, which is amorphous. Okay, so for the moment, we are not going to worry about crystallites. Just what happens as you increase the temperature. So, the modulus varies over quite a large range. And what is the modulus? The modulus is the, remember from mechanics you have the force equals kx for a spring. The modulus is k for a three-dimensional material. It's the proportionality constant that says how much of material is going to pull back or push out versus a tensile or compressive external applied force. And what is a typical value of a modulus? So this might be maybe a gigapascal or gigapascals. Rubber might be a megapascal. Human skin might be more like 10 to 100 kilopascals. So the modulus of atactic polystyrene, and we'll do this from 330, and you'll see why I've chosen such bizarre axis labels in a second. We start out at just above 10 to the 9th, so we're in the gigapascal regime. And then the glass transition temperature happens to be 370. So as we go toward the TG is not really an abrupt transition. Some of the polymer chains move at require different activation energies than others. In fact, unlike a TM or a TC, there's no latent heat of a glass transition. So it's more of a smooth transition from below the TG to above the TG, whereas we know in crystallization and boiling and condensation, it requires a latent heat. So an amount of material at its boiling temperature requires an additional amount of energy to break all the bonds, and that's called the latent heat. And that's a first order phase transition. In the case of a glass transition, it's more of a gradual transition. So right in the vicinity of the TG, it starts to go down, and then maybe it's here, and then you have this rubbery regime, then it's rubbery flow, and then it's a pure liquid. So what do we have here? This is the glass transition. And up here, it's glassy. And these distinctions are a little bit loose, but they kind of have fun names. This is leathery. The regime here, where it doesn't change much, is rubbery. Then we have some more flow in the system. So we call this rubbery flow. Then you have a pure viscous response, which has very little elastic recovery in the system. So high elastic recovery, very low elastic recovery. What happens when we put a material in a pull tester, where we take, say, a block of a polymer sample and we pull on it and we measure the force as a function of the extension. So we stretch out the sample, we measure the force that it takes to stretch it out. So mechanical properties. What we're going to do is take a specimen with cross-sectional area that looks like this, and it is defined by cross-sectional area A and length, initial length L naught, and we are going to stretch it and we have L naught and delta L. Now I've drawn this as quite a large deformation, but this is really going to, polymer samples are really going to respond elastically under relatively short deformations, like 10%-ish, depending on the material. And we will define stress, which is sigma, and that is the applied force over the area perpendicular to the stretched axis. And the strain, so stress is sigma, strain is epsilon, and that is delta L over L naught. And sometimes this is written as a percentage, sometimes it's written as a fraction, and it will tell you which it is. And then the another quantity is the Poisson ratio, which is nu, which is the fractional contraction of the transverse axis relative to the deformation of the longitudinal axis. What? It means that if you stretch it by 10%, one of the cross-sectional dimensions shrinks by 5%. If the Poisson ratio is a half, is 0.5. The Poisson ratio is the fractional contraction of transverse axis relative to deformation, let's say stretching, if we're just talking about tensile loading. Okay, so it just means the x or y coordinate shrinks by some fraction relative to the amount that the z coordinate stretches. You stretch by If a Poisson ratio is 0.5 and you stretch by 10%, that means that the transverse axes both shrunk by 5%. So what we are going to do is plot a generic stress strain curve in pascals or newtons per meter, square meter, as a function of strain. Now, what happens as we pull apart a polymer sample is at the beginning, suppose this is a semicrystalline polymer sample. And when I draw this plot, it's not like all semicrystalline samples are going to have the same stress strain curve, or even some of them don't even exhibit all the same features as the stress strain curve I'm going to draw, but I'm going to draw a generic one and explain what's happening microstructurally. As you take a semicrystalline sample, and you can picture the simplistic version that I drew that just has some crystallites and then some amorphous material, as you stretch it out first, what's going to happen is that the amorphous chains are going to align along the axis of strain a little bit. Now, as you align polymer chains and you make them like this in the stretched out version, or you bring them toward the stretched out version, what's going to want to happen? What does a polymer want to do if it's stretched out? It wants to go back. And why does it want to go back? Entropy. So in the low strain regime, where we are aligning the polymer chains, we're forcing it to be in a low entropy state. It wants to get back to a high entropy state, and it knows that if it contracts, it has more statistical degrees of freedom. I don't know if it knows. That's like the mystery of nature, right? So, but it does. It does. It's all, there's always some oscillation, and if it goes further in, if it goes further toward the contracted state, the entropy increases. So in the elastic regime of a semicrystalline polymer or an amorphous polymer, it's actually they call it an entropic spring, because it's really a statistical argument for why the polymer film wants to contract. So in the regime of low deformation percentage, we have a straight line. And this is the elastic behavior. Then what happens is that there can be some portion where it's still elastic, but it's not quite, but it's not linearly elastic. We've passed the proportionality limit. Proportionality limit. Then something happens where the polymer sample yields. Now, what happens at the yield point? At the yield point, the polymer crystallites start to pull apart. We put in enough force to break the intermolecular forces between the polymer chains in the crystallites, and we can now stretch the material out that way. Then what happens is that there's anarchy in the system. We have all of these chains that are not aligned, but we have lost the crystallites that are holding the material together. We've started to kind of destroy them, so the stress might go down a little bit here. But then as the polymer chains start to realign, because we're stretching it more, we've destroyed the crystallites, but now we're stretching it out and we're actually producing new crystallites, but now the polymer chain axes are going to be parallel to the axis of strain, which is going to strengthen the material. So then the polymer chains are increasingly aligned with the axis of strain. But then we get to a point here where polymer chains start to pull out of the crystallites and bonds begin to break. Because we've put so much strain in, and polymer has some finite amount of energy it can absorb before it breaks apart. And this is called the ultimate tensile strength. And then it gets to a point where some combination of chains pulling out of the crystallites or past each other, or chain scission events, which happens in glassy polymers and purely cross-linked polymers, where you can't break the material without actually breaking covalent bonds in the solid, then it dies here. Okay, let's name some of the key features here. The slope here is called the modulus. This is the tensile modulus in the case where we're stretching it. Tensile modulus is also called the Young's modulus of a material. It's the most common flavor of moduluses. And this region here, the integration of the stress strain curve in the elastic regime, is called the resilience. So this is an energy density. In units of joules per cubic meter and SI units. And this is the area under the curve. We get to the point here, which is the elastic limit looking to the left. Or the yield point looking to the right. I have never been able to find a good explanation for if they should be two separate points or if they're just infinitesimally separated. I think they're infinitesimally separated. Question?
The terminology difference, like boiling point, condensation point, they mean the same thing but from different perspectives?
Yeah, they basically mean the same thing, but from different perspectives.
If you're in the elastic regime and you're pulling harder, you're going to call it the yield point, and if you're going the other way, it would be called the elastic point. Like the arrow indicates perspective.
Yes, yeah, because you can't have yielded if you're still in the elastic regime, which is implied by elastic limit. This is as far as I can go while still being elastic. And did I make an error?
No, I was just wondering if it's a little bit more clear to say where the slope changes. If it's an inflection point.
Yeah, so a lot of stuff happens between the proportionality limit, where it's still, in a real sample, these points are very close to each other, but we're not going to worry about the distinction for our purposes. There's a region of proportionality, then there's an elastic limit, then there's a yield point, and they can occur they occur over very, very short strains.
Just to clarify, we're calling the integrated area there, that's the elastic regime?
Yes. The integrated area here is the elastic regime. This point here, if the material has one, is a lower yield point. Up here, we have the ultimate tensile strength. Which is the quotient of stress over strain at this point. Then we have this fracture, and the fracture stress is called the fracture stress. The fracture strain, however, is called the strain at fracture. Or the fracture strain. Or the elongation at break. Same thing. Now the entire curve you can integrate as well, which includes the resilience and then all this stuff here. And the area under the entire curve is called the toughness. This is the total energy density absorbed prior to fracture. And that is, again, the integration of the entire stress strain curve is the toughness. Now, interestingly, that includes the resilience. So the resilience is always smaller than the toughness. The resilience goes into this calculation of the toughness. And if you hear words like store or dissipate mechanical energy, if the mechanical energy is stored, you're in this regime. But then as soon as you pass the yield point, all of that energy that's been stored is now absorbed by the material.
We were like stretching a metal or something.
If you're stretching a metal, or in this case, stretching a polymer.
Because it will retain that shape afterward.
Yes, yeah. So this is all plastic deformation, and this is elastic deformation. Okay, what are the nanoscale changes that occur during these different deformations? So in the elastic regime, the chains straighten out and entropy provides the restoring force. What about materials that are mostly crystalline? There's some deformation of the crystallites as well. And the deformation of the crystallites, the restoring force has nothing to do with entropy. It's that we're moving the polymer chains farther apart, but because of van der Waals forces, they want to move back together in a tensile modality. In a compressive mode of deformation, it's because the atoms are getting too close to each other. And you can't have atoms get too close to each other. There's a steric repulsive force that pushes them apart. I should make that sound not the same one that I use for my alarm clock. At yield, you are pulling apart the crystallites. This regime here is strengthening. And strengthening occurs by realignment of chains. And fracture is a result of chain pullout and bond scission. Any questions in the last 1 minute? Yep.
Does fracture start occurring at the nanoscale at the ultimate tensile strength?
Yes. So elements of, so this is where the material completely bifurcates, and actually the damage to the film in the form of, or damage to the specimen in the form of chain pullout and bond scission starts occurring after the ultimate tensile strength. All right, thank you very much. We will begin on Friday with a discussion, with a primer on biological structures at the nanoscale.